You just did the standing waves lab. We've kind of talked about these things as constructive, destructive interference stuff, but I want to like formalize it today. I also want to add in a couple of other things that we want to write down and then do some examples and things and make sure that you're feeling confident about it. We are going to have a couple questions for homework today that will just build on what we're doing. It all just helps. It all just goes together. So here we go. Just a couple of concepts, a couple of things that we've mentioned, but bear repeating. There we go. Two waves that travel in the same medium. I want you to imagine or think about a time when you've seen two waves traveling in the same medium. We know some things about them. One question that I have is if you have two waves, so two disturbances traveling through the same stuff, right? Medium just means the material or the stuff that it's traveling through. How do the speeds of those waves compare? These could be sound waves. These could be waves going on a slinky, waves in the water. How do the speeds compare? Do you know? Or do they depend on something? Is that like a bright light? Think about when you were doing the snapping lab, right? Do you remember we measured the speed of sound? Does that sound familiar to you? Yeah? And you had to find the theoretical speed of sound. How did you do that?
331 plus
something, right?
Times.
Yeah. So there's some funny equation, but the equation is dependent on what? Is it dependent on the frequency of the wave? You just recited it to me. The equation, does it depend on the frequency of the wave? Depends on the temperature, right?
Yeah.
It only depends on the temperature, which means that any sound wave is going to travel at the same, what? Speed. Yeah. It's going to travel at the same speed. So two waves traveling the same medium. So that could be a sound wave traveling through air. That could be a wave traveling through a slinky. That could be a water wave traveling through, well, water, okay? In any of those cases, the waves travel at the same speed, okay? The frequency of the wave does not matter. Okay? Let that sink in for a minute. Don't just turn your brains off, but think about what that means. Two waves traveling in air, two sound waves, travel at the same speed. That means they cover the same amount of distance in the same amount of time, right? That's what speed is. Same amount of distance over the same amount of time. It's really, really good that this is true. You experience this all the time. But the best example of this is when you go to some sort of musical concert. Okay? If you've ever been to an orchestra concert or a band concert or a choir concert or a concert for your favorite musical group, like it does not matter. It doesn't have to be classical music, right? In any case, if you have two performers or more performers on stage, and they're cued by the director at the same time, one of them has a really, really high frequency, one of them has a really, really low frequency, right? You have two different sounds. Which one's going to get to you first?
You're going to get there at the same time.
You're going to get there at the same time, right? Trick question, big air quotes, right? They're going to travel the same distance in the same amount of time, so they're going to get to your ear at the same time. You can think about it in way, if you had some waves that travel faster than others, especially if you were sitting way in the nosebleed section, right? If you're at a really, really big venue, you're at the way, way back. If it took longer for, I don't know, the low frequency waves to get to you, you would hear a huge distortion between the high pitch and the low pitch. Are you with me there? Does that kind of make sense? It's important to know that no matter the frequency, the waves travel at the same speed. Always. That's true both for sound waves, but it's also true for waves in a slinky. Okay? Or waves on a string. Any of those things. That's the first piece that I really want to make sure that you know. The second thing that I really want to make sure that you know is that if those two waves interact, if they happen to be at the same place, can they occupy the same space at the same time? Or no? Yeah. They absolutely can. We did this out in the hallway. We had that big, long slinky. Do you remember? We had that big, long slinky, and we had one side over here. Oh, come on, silly thing. And maybe there was a wave like this, and it was traveling this direction. And then over here, we had a wave like this. Hello. And it was traveling in this direction. Okay, they're on the same string, by the way. My goodness. When they get to each other, if you have two, I don't know, like basketballs that are rolling towards one another, can two basketballs occupy the same space at the same time? No. What are they going to do? What are the basketballs going to do, friends? They're going to bounce off, right? Elastic collision. Absolutely. Matter cannot occupy the same space at the same time, so there's going to be a collision, there's going to be a force, there's going to be something. Waves are different because waves are just transmitting energy. And different amounts of energy can be at the same space at the same time. Absolutely, this can happen. Okay? So that's the other piece here, is that two waves traveling in the same medium, they can occupy the same space at the same time. Oh my gosh. Again, that's good, right? Again, this comes back to that music concert. If two waves couldn't occupy the same space at the same time, then they couldn't cross. And so then if you were sitting on one side of the auditorium and the flutes were on the other side of the auditorium, they would have to cross a whole lot of other waves to get to you. And if they can't, you would never hear the pretty flute music. Okay? You just wouldn't hear it. It would be gone. Okay? Absolutely, those two waves can occupy the same space at the same time. And after they do, what do? Do they bounce off of each other like the basketballs? They add when they're in the same space. And then what? They become one, or they just stay there? They do? And then do they just stay there, though?
No, they keep going.
They just keep on going. Waves are funny. They just keep on moving. It's like there was nothing there. Right? It's like there was nothing there. Okay? Let's talk about that. So when we have them occupying the same space at the same time, this is exactly what we were just talking about. Okay? What happens is this fancy pants thing. I feel like I need some sort of graphic artist. Does anybody know a graphic artist that I could hire? I would like them to make me a new superhero. I'm not even really a superhero person, but I feel like this needs to be a thing. And the superhero, it needs to be Superposition. If you're looking for an art project and you'd like to, I would, like to commission somebody to make something called Superposition, right? Superposition just means that you have two waves occupying the same space at the same time. That's all it is. It's just a fancy word for it, okay? When those waves occupy the same space at the same time, the amplitude, oops, oh my goodness. Hey, what's amplitude before I move on? I'm just using all kinds of wave words today. I want to make sure we know what they are. What's that?
The height away from equilibrium.
The height or the distance from equilibrium, right? Yeah. We're not judging. The amplitude is the height from equilibrium. When those two waves are in the same space at the same time, the amplitude is the sum of the individual amplitudes. And we're going to have a chance to do that in just a second, but I want to define a couple more pieces for this. Okay? That's as simple as it is. You're just going to add them up. Life is good. Okay? Now, we can kind of separate these into two cases. You could have a situation where you've got two waves that have displacement on the same side of equilibrium, in which case they're going to add, they're going to get bigger, bigger, bigger. Or you can have a situation where they're on opposite sides. So let's look at each of those individually. So let's do same side here. So I'm going to do one little wave going like this. And so I'm kind of drawing the that I had before. One wave coming like this. So they're coming at each other. Boom, boom. And again, just to make this all really clear. So here's the amplitude for this one. And there's my equilibrium point. Here's the amplitude. We'll call it A1 plus A2. When those two waves get to the same spot, we have what we call constructive interference. Okay. In a situation of constructive interference, the sum, since they're both up, they're both positive, the amplitude is going to be bigger than either one was before, right? So the amplitude is going to increase so it'd be like A1 plus A2. Okay. And the result of an increased amplitude, so it means that the wave, if it's just like a wave on a string, means that it's going to get bigger. If it's a wave, a sound wave, what do you think that's going to do? If you've got two waves that are undergoing constructive interference, what's that going to do to the sound? What do you think might happen? It's going to be louder. Yeah. So it's going to be bigger or it's going to be louder. What's that? More speakers, absolutely. If you have one speaker and you're listening to it, put another speaker playing the same thing, and you sit equally between them, then you're going to get two waves at the same time that are coming from opposite directions, right? With the same displacement, it's going to be a louder experience for you.
Oh,
yeah. Yeah. Now, there are some funny things that happen depending on where you sit. And there are audio engineers that, like, this is their entire job, okay, is to figure out space, like in music venues especially. You can get places where you'll be at a crest of one and a trough of another, and, oh, that's going to be this other thing. What's that called, do you think? If this is constructive interference, what was this called? Destructive. And you can get these places, these spots where you can't hear anything. They're called dead spots in an auditorium. And it wouldn't be like silent. It's not like you would never hear anything. But you would get spots where for certain frequencies you can't hear it anymore. Right? And as an audio engineer, somebody who's trying to make a concert venue, that would be a spot you don't want to have a person sitting, right? Somebody that pays lots of money to go see your concert. So that's kind of interesting. So bigger, louder. If it's a light wave, what do you think an increase in amplitude is going to do? What's it going to do? It's going to be brighter. Mm-hmm. So that's the constructive interference thing. The opposite of that would be if they're going opposite directions. So that may mean that you have one wave like this. So this is on the opposite side of the equilibrium. And then maybe I've got one that looks like this coming this way. Okay. Again, just to make sure that we see it and we understand, this right here is the amplitude, and this right here is the amplitude. We'll call that A1 and A2. Okay. In this case, when you've got displacement on opposite sides of the equilibrium, then you've got what we call destructive interference. What happens to the amplitude? What do you do with those values? You're going to subtract them, right? You're going to subtract. Or you're going to know that one is a negative and one is a positive and add them together, right? Adding the opposite kind of a deal, right? That's going to result in a decrease in amplitude. Okay? And that's kind of a general statement. If this one is 5 and this one is 2, when they combine, what's the result going to be? It's going to be under the equilibrium 3, right? So I don't want you to get confused because this one was the resultant was 3 and this one is 2. So it got bigger. You see what I'm saying? But it's down here. So this one's getting smaller as a result of that. Okay. I just don't want you to get lost in the idiosyncrasy there. So it's going to decrease in amplitude. So you're going to add the opposites because, one of them would be negative. And as a result, the amplitude is going to get smaller. It's a decrease in amplitude. Oh, and by the way, well, here, hold on a second. Let's write this part out first. So it's going to be smaller. If it's a sound wave, what's going to happen to that sound? Is it going to get louder? Probably going to get quieter, right? And the opposite of getting brighter, if you have constructive interference, we're going to have dimmer. Yeah. Now, there is a special case of this destructive interference business. Because in the one that I drew here, you've got one that's big and one that's small. But what if they're exactly the same size? What's going to happen if they're exactly the same size? So let's say that I've got this wave. It's not a black hole. Good guess. I appreciate your idea. So if we have A1, and then I've got another one over here, trying to draw these the same. I'm never quite great at that, but I'll call it A1 as well. You with me there? So there's one that's up and one that's down. They're the same size. When they overlap, for that split second, because it doesn't last very long, but for that split second at that place where they overlap, what is the resultant amplitude? 0. It is. It is. So this is called completely destructive, okay, or total destructive. And it results in an amplitude, of 0. Again, this is only for a split second. It's only at that spot right between them where they would overlap completely. Because remember, waves can occupy the same space at the same time, and then they just keep going. You with me there? So if this is a sound wave, and I'm sitting right here, I'm going to hear A1 come by, right? And then a little while later, I'm going to hear A2, or this second A1, I guess, come by, the below one, okay? And I would hear them as if there's no big deal. But if somebody happens to be sitting, need more colors equals more fun. There we go. If I have another person who's sitting right here, right at that spot where they happen to overlap exactly, they would not hear anything. It's weird. It's a little weird. We doing okay so far? Okay. Got a couple of ranking task type things because I know you've missed them for a while. It's the first ranking task set that we've done all trimester. It's been a while. I know you've been like, where are the ranking tasks? I know. They're fun, right? It's a good way of thinking. This one isn't actually a ranking task. It's a, I don't know what they call them, decide it task. But anyway, here it comes. Two pulses travel toward each other. Hey, it looks kind of like the picture I drew just a minute ago. Pulse A happens to be wider than pulse B, but it's not as high. The question says, is the speed of the pulse A larger than, smaller than, or equal to the speed of pulse B? Or there's not enough information to tell us. Ben, you think you have an answer already? That was fast.
Wouldn't it be the same?
Wouldn't it be the same, he says?
Well,
what do you guys think?
They're going at the same time, right?
Sure.
In the same place.
Sure.
And
through the same what?
Through the same medium.
Through the same medium. And so
They're the same.
they're the same. Yeah. It's not intended to be a tricky question, but it's intended to be a make sure we're paying attention question, right? So in upper level physics, and not even in AP, we don't do this in AP, maybe in 2, I can't remember, we can actually calculate how fast a wave goes through a string, depending on the tightness or the tension in the string, and like the weight of the string, like you can do the math to figure it out. We're not going to do that. All you need to know is, if you have a string, or a slinky, or a whatever, and you've got waves traveling through it, they're all going to travel at the same speed. That's it. Simple enough? Like, it's pretty straightforward. It's pretty simple. Keep that in your brain. All right, here's number 2. This one is an actual ranking task. So your love for them can be fulfilled here. So you've got transverse waves. Transverse, hey, well, what does that mean?
Yeah.
Perpendicular, right? So you got that. I'm just friendly reminder. Wow, it's like, that's pretty great what's happening over here. Transverse, if you flip over transverse, it is a perpendicular sign, right? Perpendicular meaning that the material, the medium is moving perpendicular to the wave motion. So the material that this is traveling through, or the material is the string or the whatever, okay, is moving up and down, whereas the wave is moving in the direction of the arrow. Just want to make sure that we've really got these definitions down. A rectangular transverse wave or wave pulses are traveling toward each other along a string. The grids are shown in the background. They're all identical, so no like funny business there, okay? The pulses vary in height and in length. The pulses will meet and interact soon after they're in the positions. Okay, does that make sense? They're following their arrows. They have not interacted yet. The task asks you to rank the maximum amplitude of the string at the instant that the positions of the centers of the two pulses coincide. Okay? So I'm going to give you just a minute to think about that. I'm going to get you some whiteboards because I think it's a good day for whiteboards. So go ahead and do your thing. Think about it. Show me what you've got, my friends. A, B, C, D, A, B, C, D, you don't.
We didn't finish.
Oh, you have A, B. Okay, so I see everybody has said that A is greater than B. Except my stylist doesn't like it. Tell me why you got A and B. Let's start there. Why do you think A is going to be the biggest?
Both on top, above equilibrium, and you just add them together.
Okay, so we got constructive interference. Is that okay?
Yeah.
Constructive interference. You've got 1, 2, 3, 4, and you've got a 2. So what's their total amplitude going to be? Boom! All right. Then you've got B. Is B constructive or destructive interference? Also constructive. And what's the total amplitude going to be for that one? Yep. Or the maximum amplitude, I should say. When these two cross, when they interact, because this one is 4 wide and this one's only 2 wide, the resultant wave, when they actually interact, would look something like this. Let me see if I can draw this here. So it would be like, am I doing this right? Does that look right to you? Like that. Because you're going to have the 4 wide and then the, yeah, because that's 2 and 2. So it's going to be like that. Does that make sense? It looks kind of funny, but that's what it would look like. All right, now, hold on, we got another one. So then C and D, are they constructive or destructive? They're both destructive. Why, or what's going to happen in D? Let me ask that first. Totally destructive, isn't it? So that one's going to have an amplitude of 0. 0 is probably going to be the smallest. I don't know. What do you think is going to happen in D? C C, you've got a maximum or a -2 here and a +4. So what's going to happen to that part? What's going to happen in C?
It's going to be too high above equilibrium.
Too high above equilibrium. 1, 2, like that.
How's it? When you put-
And then that one's going to be like this, isn't it?
Yeah.
Whoops, that didn't go over the right amount, but you get the idea. Like that. Yep. It's going to be weird. Yeah. 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 But the maximum amplitude there is going to be bigger than 0. So that, yeah. How are we doing, team? Doing okay? Hey. All right. What I'm going to have you do, we don't have a lot of time, but I would like you to draw one more thing for me real quick. So we've got a jumping off point for next time. So on your notes in the next spot that you've got, I would like for you to draw a standing wave with 4 antinodes and, or excuse me, 3 antinodes and 4 nodes. Can you do that? Draw a standing wave with 4 nodes and 3 antinodes. And if you're going, what in the world does that mean? Talk to your table mates. Talk to your table mates.
You say 4?
I did. Draw yourself a standing wave with 4 nodes and 3 antinodes. And then next to one of the nodes, put a little arrow and label it node. And next to one of the antinodes, put a little arrow and label it antinode.
That's 3 inches.
Wait, 4 antinodes?
4 nodes, 3 antinodes. And then the bell's going to ring. You can leave your whiteboards where they're at. I will see you tomorrow, and we'll jump in here tomorrow.
Listen, like a node doesn't matter if it's above or below.
A node is a spot of no movement.
An antinode, sorry.
They're going to be up and down.
Okay.
Yep. Oh, so it looks like a little, like a bunch of footballs
So
sitting
it
next to each
doesn't
other.
matter then if they're above or below.
Correct.
Okay.
Well, I mean,
Like,
it
it
does in that they're
matters,
going to be
but
both.
It doesn't mean that they're not.